Welcome to this eLearn Security video on Android application reverse engineering. In this video, we're going to see different tools and techniques that allow us to decompile and disassemble Android applications in different formats. You should note that the APK is the file format used to distribute and install Android applications, and that we can investigate these files by changing their extension from .apk to .zip. This allows us to open the archive and get the files contained in it, but since they have been compiled and packed, we cannot directly read the files. For our test, we're going to use an application called re_app. Here we have the APK file, so let's first change its extension into zip. Now if we open the archive, we can see the files contained in it. Let's extract one. Let's pick the Android manifest.xml file. If we try to open this file with the text editor, we can see that it fails. We cannot see the content since it has been compiled. The same thing happens with the other files. So we have to find a way to decompile this package in order to get a readable version of the files. The first tool that we are going to use is called DexDump, which allows us to obtain the Davlik virtual machine bytecode from a DEX file. DexDump is available in the Android SDK installation folder. Depending on the version of the SDK, it may be found in the Platform Tools folder as well as the Build Tools folder. Let's run the tool without specifying any option to get all the commands available. We can see that it offers options such as to verify the checksum of the DEX file or display the file header details. But we are interested in the option -D, which allows us to disassemble the code. Since the tool needs a .dex file as input, we first need to extract the classes.dex file from the package. So let's extract it on the desktop and then run the following command. Our command will be dexdump -D classes.dex pipe to more. The output is the Davlik bytecode. But as we can see, it's very hard to read and understand. Since there are other tools that provide better output, we will not focus on this result. One of these tools is called APK Tool. APK Tool is a command line tool specifically designed for reverse engineering Android binaries. It's capable of decoding the application resources to nearly their original form. So let's open the command line and run the tool with the -H option in order to print the help contents. We can see we have a few different options. For example, we could decode or build an APK file. For now, let's focus on decoding Android applications. To do this, we have to use the option D without using any other specifying option. So let's write our command. APK tool -D followed by the path of our APK re_app.apk file, and then let's set the output directory. As soon as we hit return, the tool starts its operation, and when it finishes, a new folder containing all the decoded files is created. During this process, the tool extracts all the classes contained in the APK file and disassembles them in Smalley syntax. We will talk about Smalley shortly. Let's first open the folder just created and see what's in there. Every time an APK file is disassembled, APK Tool creates a few different files and folders. The res folder contains all of the decompiled resources that were present in the original project. This includes logos, images, media files, layouts, and much more. The Smalley folder contains the disassembled application files, while the Android Manifest is a decoded version of the original Android Manifest.xml. So let's first investigate this file. As we can see, we are now able to open and read the content of the manifest into our text reader. So let's compare it with the original file and see if they are the same. As we can see, they are very similar. Only a small amount of information is missing in the decoded version. Here, for example, only the Uses SDK node is missing. As we will see, information contained in the Android Manifest may be very useful for our security testing. Now that we know that the manifest has been successfully decoded in something very similar to the original file, let's inspect the folder Smalley. Before we go too far, let's shed some light on what Smalley is. Smalley is a human-readable assembler and disassembler for .dex files. As we have seen before, the DexDump output is very hard to read and analyze, but thanks to Smalley, now we have a human-readable, disassembled version of the app. In the Smalley folder, we can find many other folders that somehow define the application package name. Here indeed we have COM, then eLearn Security, and then the REApp. This is exactly the package name defined in the manifest. In the last folder, we have some files with the .smalley extension. Each of these files corresponds to a Java class defined in the files contained in the source and gen folders of our original project. Files with the $sign are inner classes. So now that we know the structure of the folders and files created, let's open the Java class reverseengineering.java and the corresponding reverseengineering.smalley file. At the very beginning of the file, we have the class declaration. We can see the full path of the class, its name, as well as the name of the class that it extends, in this case the activity class. Right after these three lines, we can find the constructor method. .local0 indicates the number of non-parameter registers within the method. Line 9 indicates that the next operation is defined at that specific line in the source code. So this operation is defined at line 9 in the source code. The invoke indirect is used to invoke a non-static direct method, and P0 is the parameter. What follows is the object and method to call. Here the L at the beginning indicates an object, while the V at the end of this line indicates the void primitive of the method. Android/app is the package name. Activity is the object name. What follows the arrow is the method to call. So in this case, it is calling the init method from the class activity. The last operation of this method is return-void, which, as you can imagine, returns from a void method. Let's now take a look at the method sayHello and see the differences between the Smalley version and the original code. This will help us to better understand Smalley. In the source code, we see that it is defined as public and its returning value is void. We can see the same information in the Smalley version. Here we can see that it is defined as public, while at the end of the line, The V indicates that its returning value is void. Here we have the name of the method and its parameters, while in Smalley we have the name of the method and then the object type of the parameter. The name of the parameter is defined a few lines after. At line 26, the method implementation. We can see that this line has been decoded in Smalley with a few different operations where the method findByViewID is called and then the result of this invoke is moved into the register V0. After that, the checkCast verifies that the object reference is an instance of TextView. Now at line 27, we call setText on the text object with the following string. If we look at the Smalley version, we can see that the register V0 contains the text object, and then the const string operation moves a reference to the string reverse engineering hello into the register V1. At the end of the method, setText is invoked, and the previous two registers are used as parameters. So as we've seen, APKTool allows us to decompile the application binary in a better readable form, unlike the DEXDump output, which is very hard to understand. If Smalley doesn't fit our needs, we still have another option to decompile Android applications. This method returns a very high-level format that is very similar to the actual source code. To do this, we will use a command line tool called dex2jar, which decompiles DEX files into jar files. In the same way as we did for the previous tools, let's run the dex2jar command without any options. As we can see from the output, the correct syntax to use is d2j-dex2jar.bat, followed by the APK file we want to decompile. Once again, let's use the application re_app.apk. The option -o to set the output option, followed by the path of the output file. Once the tool ends its decompiling process, we will have a new jar file on the machine. In order to inspect its contents, we need a Java decompiler. In this video, we're going to use a free tool called JD-GUI. Let's open JD-GUI and then select the jar file that's been created with dex2jar. We have all the files obtained with the previous tool, and we have the application package tree, and within the package we can see the classes build config, reverse engineering, and R. If we open the content of these files, we can see that the content is almost the same as the source code. Let's try to compare this file with our original code. As we can see, they are very similar, but not completely equal. Notice that within the full name of the resource, there are some numeric values. As we will see in a few moments, those resources are defined in the R class. As seen in the sayHello method, there are some differences. Noticeable here is that the two instructions defined in the source code are now joined together. In the source code, we can see that the method findViewById has the parameter TextView2, while in the decompiled version, we have this number. So let's copy the number and let's go to the class R. Let's click Edit, then select Find, and then paste the value. As we can see in the R value, we can find all the values defined in the other methods, and we can get the corresponding resources, in this case, which is TextView2. So as we have seen, this last method is actually the best way to get decompiled version of the app, since it's virtually the same as the source code. Now that we know how to decompile an Android application into a very high-level form, we can try to understand the logic behind the applications. We can search for vulnerable implementations, hard-coded information, and much more. In this video, we have seen a few different techniques and tools that allow us to disassemble and decompile Android applications. and depending on the tool we use, the different formats that can be obtained. We advise you to create a few apps with different implementations and then use these techniques to verify how these tools decompile the applications. Thanks for joining us.